The unexplained disappearance of hundreds of vials containing highly infectious viruses from an Australian laboratory has raised serious concerns regarding biosecurity and the oversight of hazardous materials. This troubling event, confirmed by an official report released at the end of 2024, involved the vanishing of 323 vials from Queensland's Public Health Virology Laboratory. These vials contained dangerous pathogens including hendrovirus, hantavirus, and lissavirus. The incident has prompted widespread unease among both public health officials and the broader community, as questions mount about how such a significant breach could have occurred and what consequences may still be unfolding. In a surprising twist, the hacking group Anonymous claimed on social media that they had uncovered internal documents related to the missing virus vials from the Australian laboratory. According to their posts, the documents revealed inconsistencies in inventory logs and internal communications that allegedly showed officials knew about the disappearance months before it was publicly disclosed. Anonymous suggested that the breach had been quietly downplayed to avoid public panic. Their revelations quickly gained attention, sparking renewed concerns about transparency, accountability, and the possibility of a cover-up. The issue first came to light in the year 2021, when a malfunction was reported in one of the laboratory's freezers. This prompted a closer inspection of the contents, ultimately revealing that several vials were unaccounted for. However, it was not until August of 2023 that investigators officially confirmed the disappearance of the samples. This long delay between the initial discovery and the formal acknowledgement of the breach sparked frustration, as many felt the situation had not been handled with the urgency it warranted. Queensland's Health Minister Tim Nicholls addressed public concerns by noting that while these viruses could, in theory, be used to cause harm, doing so would require an advanced level of scientific expertise. Thus, the immediate risk to the public was considered low. Nevertheless, the inability to verify whether the samples had been destroyed, relocated, or taken has led to growing unease over the protocols in place to secure such sensitive materials. The absence of proper record-keeping and the lack of transparency have left many wondering how closely these facilities are being monitored. Queensland's Chief Health Officer, John Gerard, suggested that the missing samples may have been transferred to another freezer without accurate documentation. Alternatively, they may have been disposed of incorrectly or destroyed during a routine sterilization process. Yet without proper records, these theories remain speculative. Investigators could not confirm with confidence whether the vials had been accounted for or were still untraceable, and this ambiguity continues to cast a shadow over the laboratory's operations. The pathogens involved in this case are among the most serious known to science. Hendrovirus, first identified in the year 1994, is a zoonotic virus primarily transmitted by fruit bats and known to infect horses and humans. In human cases, it carries a notably high mortality rate of around 57%. Hantavirus, another zoonotic threat, originates in rodents and is transmitted to humans through contact with contaminated fluids or inhalation of aerosolized particles. The resulting illness, hantavirus pulmonary syndrome, can lead to severe respiratory distress and has a fatality rate of nearly 38%. Lissavirus, closely related to rabies, is almost invariably fatal once symptoms begin to manifest. Its presence among the missing samples is especially alarming, given its extreme severity. Despite the potential danger posed by these viruses, Queensland health officials have emphasised that there is no immediate public threat. Dr. Gerard explained that such viruses degrade rapidly outside controlled environments. Without proper freezing, the pathogens would lose their infectious capability within a short span of time. He also speculated that the missing vials may have been unintentionally destroyed in an autoclave, a standard procedure used in laboratories to neutralize hazardous biological materials. Still, the fact that such a process was not documented adds to the uncertainty and public concern. One of the most troubling elements of this incident is the significant bureaucratic delay. It took approximately 1 year for investigators to receive clearance to inspect the malfunctioning freezer, during which time no meaningful progress was made in locating the samples. This lag in response has been heavily criticized by both the scientific community and members of the public, who believe that such matters should be dealt with swiftly and transparently. The delayed investigation suggests that more rigorous protocols are urgently needed to handle and track sensitive biological materials. This incident has sparked broader discussions about how laboratories safeguard dangerous pathogens. It has become increasingly clear that relying on manual documentation and outdated tracking systems leaves too much room for human error. Experts are now advocating for stricter regulations, improved technological oversight, and faster response mechanisms to ensure that any future discrepancies are caught and resolved without delay. While there is currently no direct evidence to suggest that the vials were deliberately removed or taken for harmful purposes, the mere possibility is enough to alarm both authorities and the public. In a time when concerns over bioterrorism, laboratory leaks, and the potential misuse of scientific knowledge are growing, even a small breach can have significant implications. The uncertainty surrounding the fate of the missing samples reveals how critical it is for laboratories handling infectious agents to maintain impeccable standards of accountability. Officials continue to assert that the situation poses no danger to public health. However, the lack of definitive answers leaves open a range of possibilities. Whether the disappearance was the result of simple mismanagement, procedural oversight, or something more troubling. The fact remains that 323 vials containing some of the world's most dangerous viruses went missing without explanation. Until conclusive evidence proves that the vials were rendered harmless or properly destroyed, this incident will likely continue to fuel speculation. It serves as a cautionary tale about the challenges and responsibilities that come with working in the realm of virology and biosecurity. The scientific community and regulatory bodies alike must take the lessons from this event seriously, ensuring that stricter oversight, better documentation, and enhanced response protocols become the new standard. In the meantime, the mysterious case of the missing virus vials stands as a stark reminder of the importance of vigilance when dealing with materials that could, if mishandled, have far-reaching consequences. The mysterious disappearance of hundreds of vials containing dangerous viruses from an Australian laboratory has sparked a wave of concern, not just for the breach itself, but for what it could mean if these pathogens were ever released into the public. While officials have attempted to reassure the public that the threat is minimal, many are not convinced. The idea that deadly viruses like Hendra, hantavirus, or lyssavirus could be mishandled, misplaced, or deliberately released has left people uneasy. Even more troubling is the thought that such a release could occur quietly, without the public ever realizing what was happening until it was too late. One of the core fears is how easily a pathogen could spread before anyone became aware of it. Many viruses have incubation periods where symptoms do not appear immediately, allowing a person to unknowingly infect others. If one of the missing samples somehow made it into circulation, either accidentally or through more intentional means, it could silently move through communities. With symptoms often mimicking those of common illnesses, an outbreak could be mistaken for something far less serious, giving it time to grow and spread before any containment efforts began. The worry isn't just about accidents or poor oversight. Some fear the potential for these viruses to fall into the wrong hands. With global concerns about biosecurity and bioterrorism already on the rise, the idea that lethal pathogens could simply vanish from a secure facility raises questions about who might have access to them and what their intentions could be. While using such viruses effectively would require significant expertise, history has shown that underestimated threats often cause the most damage. Even a single mishandled vial could trigger a situation with devastating consequences. There is also concern about transparency and trust. If a release did occur, would the public be told? In the past, some authorities have hesitated to fully disclose health risks out of fear of causing panic. This has led to speculation that a slow-moving or localized outbreak might be explained away or minimized until it became unmanageable. In an era where public trust in institutions is already fragile, the possibility of hidden dangers and withheld information only fuels suspicion. In the end, the true danger may not be the viruses themselves, but the uncertainty surrounding them. When something this serious goes unaccounted for, it forces people to imagine worst-case scenarios. Whether by accident or design, the release of even one vial could reshape lives and communities, and we may not even know it's happening until it's already too late. In a recent and widely discussed update, a member of the hacker collective known as Anonymous claimed that billions of genetically modified mosquitoes had been released into the wild without widespread public knowledge or understanding of the potential long-term consequences. This statement reignited debates surrounding genetic engineering, public health, and ecological risk. According to the information shared by this member, the Environmental Protection Agency had approved a proposal by Oxitec, a biotechnology company based in the United Kingdom, to release approximately 2.4 billion genetically modified mosquitoes over a period of 4 years, ending in 2024. This large-scale release initially began as a trial in Florida and was later expanded into California's Central Valley, a region already struggling with rising mosquito populations. The genetically modified mosquitoes released by Oxitec are exclusively male, which means they do not bite humans or animals. The technology behind this approach is based on the idea that the male mosquitoes carry a gene that prevents female offspring from surviving to adulthood. As only female mosquitoes bite and transmit diseases like malaria and dengue fever, this method is expected to significantly reduce disease transmission without the use of traditional pesticides. While the theory behind this approach appears promising, especially in terms of reducing mosquito-borne illnesses, the anonymous member warned of the deeper, less understood consequences of releasing genetically modified organisms into natural ecosystems. They emphasized that genetic interventions, even when aimed at disease prevention, must be thoroughly analyzed not only for their immediate impact, but also for their long-term ecological implications. One of the primary concerns raised by critics is the disruption of natural ecological balance. Mosquitoes, though widely considered pests, play important roles in food chains, serving as a crucial food source for birds, bats, amphibians, and other insects. If genetically modified mosquitoes successfully reduce or eliminate certain mosquito populations, these predators may struggle to find adequate food. This could trigger cascading effects through the ecosystem, with population declines in certain species and potential overpopulation in others. The disruption of these relationships can destabilize entire habitats. Another serious issue is the potential for resistance to develop among mosquito populations. Just as bacteria have developed resistance to antibiotics, it is possible that a segment of the mosquito population might survive the genetic intervention and pass along their traits to future generations. Over time, this could lead to a dominant mosquito population that is unaffected by the introduced gene, making control efforts even more difficult. Resistance development is a common concern in pest control strategies and highlights the need for constant evaluation and adaptive management. The anonymous update also drew attention to the possibility of unintended genetic consequences, particularly regarding non-target species. In natural environments, interbreeding between closely related species can occur. There is a risk that the genetically modified mosquitoes could pass on their engineered genes to other mosquito species or even to unrelated insects. This unintended gene flow could result in ecological changes that were never anticipated or accounted for during the initial risk assessment. Furthermore, beneficial insects such as pollinators may also be unintentionally affected if they come into contact with these modified organisms or share the same habitats. An additional concern is the uncontrolled spread of modified genes. Once genetically engineered organisms are introduced into the environment, it is extremely difficult to contain or reverse their impact. Gene transfer through mating could allow these traits to persist and proliferate in ways that cannot be easily monitored. If the altered genes provide a reproductive advantage, they may spread rapidly and dominate native populations, potentially altering local biodiversity and changing the character of entire ecosystems. Critics argue that while the intention behind such technologies is rooted in public health, the potential for irreversible genetic consequences is too high to be taken lightly. There is also a possibility that changes in mosquito populations could influence disease transmission in unexpected ways. While the goal is to reduce the spread of specific diseases such as dengue fever or Zika virus, decreasing one mosquito population may inadvertently create space for another vector species to rise in prevalence. This could shift the disease landscape, leading to an increase in diseases that were previously less common in the region. Disease ecology is highly complex, and any significant manipulation of vector populations should be accompanied by detailed modeling and continuous monitoring. The anonymous member stressed that while the genetic modification of mosquitoes may offer a solution to pressing public health challenges, it also opens the door to a wide range of scientific and ethical concerns. Public consent and awareness, they noted, are fundamental to the responsible use of biotechnology. In this case, many people were unaware that such large-scale releases had even begun, let alone the extent to which they had progressed. Although the Environmental Protection Agency approved the project, critics argue that more public dialogue should have taken place before moving forward with such a potentially transformative initiative. The use of genetically modified organisms in nature remains one of the most hotly contested issues in modern science. While there is no doubt that scientific innovation has the potential to solve some of humanity's most urgent problems, the speed at which these technologies are being developed and deployed has left many feeling uncertain and concerned.